All right, welcome to then we'll combine the last part of the third page and the fourth page together. And that way we'll have everything completed. And the last parts are talking about the tangential and normal components of acceleration. So when we study the motion of a particle, it's often useful to resolve the acceleration to two components, one in the direction of the tangent and then the other in the direction of the normal. And so if we write our speed as just the magnitude of a velocity vector for the speed of the particle, then our tangent vector is just going to be equal to our unit tangent vector, is equal to the derivative of the position function divided by the magnitude of the derivative of the position function, which is just going to be our vector or our velocity function divided by the magnitude of the velocity function, which is just going to be our vector function divided by speed. So what we can say is that if we solve for our vector function, we could say that our vector function is equal to our velocity times tangent a function, or our velocity times unit tangent. Now, if we differentiate both sides of this equation, what we're going to get is we'll get the acceleration, because A is equal to the V prime which is equal to, and that V is vector V. So let me bolden that. The derivative of vector V, which is just equal to, and on the right, it's going to be a product rule of velocity and tangent. So the derivative of velocity times tangent, let me just denote these, all right, times the unit tangent vector, plus the derivative of the unit tangent vector times our speed. All right. And so, denoting that V right there is just going to be speed. That doesn't have the vector notation above it. If we use the expression for the curvature, then we have our kappa is equal to the derivative of the unit tangent vector, the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position vector, which is just equal to the magnitude of the derivative of the unit tangent vector all over speed. So what we can say is that the magnitude of the unit tangent, the derivative of the unit tangent vector is equal to the curvature times speed. We define the unit normal vector was as n, so unit normal is equal to the derivative of our unit tangent divided by the magnitude of the derivative of the unit tangent. So therefore, the derivative of the unit tangent is equal to the magnitude of the derivative of the unit tangent times our normal vector, our unit normal vector, which is equal to the curvature. So now substituting in what we have over here for the derivative of the unit tangent, substituting it right here, we have the curvature times speed. So the derivative of the unit tangent is equal to the curvature times speed of the unit normal vector. And so what we get is that our acceleration is now made up of two components of the tangent and the normal vector, where the tangent is just the derivative of our speed, and the normal vector, the component of that, is going to be the curvature times our speed squared. So what we can do is now we can say, well, now we have two parts, A of t and A sub n of cap t and A sub capital N, for the tangential and normal components of acceleration. And so we have acceleration, which is equal to our A sub t of t plus A sub n of n, where A sub t is just your speed, the derivative of your speed, and A sub n is the curvature times your speed squared. So we notice that in this formula, the binormal vector B is absent. So no matter how an object moves through space, its acceleration always lies in the plane of our unit tangent and our unit normal. vectors, and so the osculating plane. So recall that t gives the direction of motion and n points in the direction the curve is turning. So we can rewrite the formulas above so that they depend only on r prime, and r double prime. So for our tangential component of acceleration, we can write that in terms of r prime of t times r prime of t dot r double prime of t all over the magnitude of r prime of t. And we can write the normal component of acceleration as the magnitude of the cross product of r prime and r double prime divided by the magnitude of r prime. So why is that? Well, if you recall what a of t is, if a of t, our tangential component, is equal to our velocity prime, well, that's just going to equal the dot product of v times a, because it's a scalar, right? So the dot product of v and a divided by our speed. So that's why we can go ahead and change what v is. So v is r prime of t dot acceleration, which is r double prime of t all over. And again, another way to write speed is going to be the magnitude of r prime of t. So that's why we're able to change the tangential. And then now the normal component, a sub n, that was equal to the curvature of our speed squared, which is equal to, now if you recall from, I guess yesterday, last class, the curvature we could write as r prime of t, the cross product, the magnitude of the cross product of r prime of t and r double prime of t over r prime of t, the magnitude of r prime of t cubed. So that's curvature. So this was what we had. That was a formula we had from yesterday when we were talking about curvature. Times speed squared, which is just r prime of t, the magnitude of r prime of t squared. So two of those r prime, so we're going to cancel out some magnitudes of r prime of t, so we're just left with the magnitude of the cross product of r prime of t and r double prime of t over just velocity. I'm not sorry, not velocity, but speed. I love how all these letters go. And that's why we're able to do this. So now, what we're doing is we're taking something that was really kind of complex, and we changed them all in terms of the derivative for the acceleration component, for the tangential and the normal components of acceleration. And so we're just going to apply that. So it's not going to be something that's going to be overly difficult. And then we're finished for today. So find the tangential and normal components of the acceleration vectors. So we have r of t is equal to 1 plus ti plus t squared minus 2tj. And so the first thing I'm going to do is I want to just find all my derivatives. So I'm going to go ahead and find the derivative of r prime. So r prime of t is equal to, so the derivative of 1 plus t is just going to be I. And then the derivative of t squared is 2t minus 2t, so minus 2j. And then let's go ahead and also find the magnitude of that. So the magnitude is going to be r prime of t, and that's going to give us the square root of 1 squared plus 2t minus 2 squared. And doing the math there, we're going to get the square root of 1 plus 2t squared, so 4t squared, 2t times negative 2 is minus 4t, so minus 8t, and then plus 4. So we should get the square root of 4t squared minus 8t plus 5. Right. Now let's find r double prime of t. So r double prime, so the second derivative is going to be r double prime of t is equal to, well, I goes away. Derivative of 2t is just 2, and derivative of 2 is 0, so 2j. Right? And then let's go ahead and do the cross product of those two, r prime of t and r double prime of t. So doing the cross product, we get write out the components of 1, 2t minus 2, 0, and 2. Cross product would just be 2. All right, and when we do the cross product, we're just going to get 2 k. So, based off of all the information that I have, I'm going to go ahead and do the tangential. So A sub cap t is going to be r prime of t dot r double prime of t all over the magnitude of r prime of t. All right. So when we do that, we are going to get cross product we said was going to be 2 and over the square root of 4t. No, whoa, I'm moving on a little too fast. So we do the dot product, which is going to be 2 times 2t minus 2. And then the denominator is just going to be the square root of 4t squared minus 8t plus 5. All right. Then the second part is going to be a sub n, which is going to be the magnitude of the cross product of the two derivatives divided by the magnitude of the derivative of r, which is just going to be 2, the square root of 2 squared is just 2 over the square root of 4t squared minus 8t plus 5. All right. And so there's our tangential component, which, I'll highlight here. And our normal component of acceleration. All right, that's it.